In arid regions facing severe freshwater scarcity, the historical solution has been brute force. For decades, global potable water in these areas has relied on fossil fuel-intensive thermal desalination facilities. This legacy approach extracts a heavy toll. By burning massive amounts of crude oil and natural gas to boil seawater, these plants generate substantial greenhouse gas emissions while discharging hypersaline brine that damages localized marine ecosystems. The economics of water extraction are shifting as the cost of renewable power drops below that of fossil fuel alternatives for over 90% of new projects. This makes it possible to finally move away from thermal distillation and towards decentralized, membrane-based purification. However, a simple connection to a solar array is often insufficient. Traditional reverse osmosis was engineered for the constant, high-pressure electrical feed provided by fossil fuel plants, creating a technical mismatch with the intermittent and variable output of a renewable grid. The industry tracks this efficiency using a precise metric, specific energy consumption, or SEC. This measures the exact number of kilowatt-hours required to produce 1 cubic meter of fresh water. This chart shows the specific energy consumption across different methods. Legacy thermal processes like multi-stage flash distillation require up to 25.5 kilowatt-hours per cubic meter. Modern seawater reverse osmosis operates between 3.0 and 6.0 kilowatt-hours per cubic meter. When directly coupled with a solar array, the carbon footprint of that cubic meter falls from 6.0 kilograms of CO2 to just 0.1 kilograms. The objective for the 21st century is to systematically eliminate the remaining hydraulic inefficiencies in these systems, driving the SEC toward its absolute thermodynamic limit of roughly 2.0 kilowatt-hours per cubic meter. Reaching that 2.0 kilowatt-hour baseline requires addressing the largest electrical draw in any standard reverse osmosis system, the high-pressure pump used to force seawater through the membranes. This chart shows the energy flow in a traditional system. Because typical recovery rates hover around 40 to 50%, half of the highly pressurized feed water exits the system as high-pressure brine, taking a massive reservoir of kinetic energy with it. To stop this kinetic energy bleed, the industry adopted a specialized component, the Isobaric Pressure Exchanger, or PX. Inside the PX is a single moving part, a highly durable alumina-ceramic rotor. It operates friction-free, hydrodynamically lubricated directly by the passing seawater. The device relies on direct positive displacement. The high-pressure waste brine makes momentary contact with the incoming low-pressure feed water inside the rotor tubes, transferring its physical pressure force almost instantly. This pressure exchange happens so rapidly that the latest generation of devices maintains a volumetric mixing rate of just 3.02%, preventing the fresh incoming feed from becoming significantly saltier. By redirecting that hydraulic pressure back to the front of the line, the workload placed on the main high-pressure pump is cut by up to 60%. Capturing and recycling up to 98% of this lost hydraulic energy single-handedly brought reverse osmosis down to a competitive energy footprint, making large-scale seawater desalination economically viable. Even with pressure exchangers installed, engineers are still optimizing the architecture of the internal fluid pathways and the molecular filters themselves. Traditional reverse osmosis operates on a continuous flow. Because the system must constantly split pressurized feed into a clean permeate stream and a waste brine stream, it suffers continuous hydraulic energy losses. This diagram compares a linear plug flow system with closed-circuit desalination, which operates as a batch process. Here, the feed water is continuously circulated under hydrostatic pressure. By recycling the concentrate through the membranes using specialized variable pressure pumps, the system extracts fresh water in periodic bursts, achieving recovery rates as high as 90 to 95% without the constant kinetic losses of a linear pipe. Scaling down from the macrofluid dynamics, the physical barriers doing the filtering, traditional polyamide membranes, impose their own hydraulic resistance. To lower that resistance, material science is moving toward advanced nanomaterials, specifically graphene oxide membranes. The molecular structure of a graphene oxide lattice allows water molecules to flow through up to 3 times faster while maintaining total salt rejection. This increase in permeability reduces the overall energy demand of the desalination process by an additional 15 to 46%, dropping the specific energy consumption into the optimized 2.3 to 2.5 kilowatt-hour range. By redesigning the internal hydraulic loops and increasing the porosity of the molecular filters, engineers are decoupling freshwater production from high fossil fuel energy inputs. While solar megaprojects require massive land footprints, regions facing acute water stress, like small island states, lack the physical space for centralized onshore solar arrays. The ocean provides a highly concentrated energy source via wave action. However, traditional designs convert mechanical wave energy into electricity just to power an electric motor that drives a mechanical pump. That multi-step conversion process is inefficient. Engineers are bypassing that loss by piloting direct mechanical wave pressurized systems, like the Ocean Oasis buoy. This schematic shows the architecture of an autonomous offshore desalination buoy. The core design utilizes a central moon pool and a floating hull. As ocean swells pass, the relative motion generated between the rising internal water column and the buoyant hull is harvested to actuate a central hydraulic piston. This piston directly pressurizes the incoming seawater to the 50 to 70 bar required for reverse osmosis. By avoiding the mechanical to mechanical conversion loop, the hydraulic efficiency is maximized. The resulting pure fresh water is then pumped autonomously back to the coast through a flexible subsea pipeline installed along the seafloor. Operating in deep water naturally reduces biological fouling, eliminating the need for harsh chemical pretreatments. It also allows coastal communities to incrementally scale their water supply without the massive initial capital expenditures of a centralized onshore plant. By translating raw ocean kinetic energy into hydraulic pressure, these direct drive architectures secure an island's water supply without requiring a connection to an electrical grid. The mechanics of extracting water from salt have largely been optimized for energy efficiency, but a severe ecological bottleneck remains on the back end of the process. Global desalination produces over 140 million cubic meters of hypersaline brine every day. When this effluent is pumped back into semi-enclosed marine systems, it destroys benthic ecosystems. Modern regulators are pushing the industry toward a strict environmental framework, Zero Liquid Discharge, or ZLD. This mandates recovering 100% of the liquid water, precipitating out only solid salt crystals for controlled disposal or mineral mining. This graph illustrates the thermodynamic friction. As brine becomes increasingly concentrated during recovery, the osmotic pressure required to separate the remaining water rises exponentially. This required force quickly surpasses the burst pressure limits of conventional reverse osmosis membranes, which typically fail around 80 bar. Crossing this physical threshold forces operators to abandon efficient membrane filtration and revert to brute force thermal brine concentrators. This incurs a massive energy penalty, requiring 50 to 70 kilowatt-hours per cubic meter to forcefully evaporate the final liquid, erasing the efficiency gains made at the front end. Preventing this spike requires advanced hybrid systems. Engineers are currently coupling ultra-high-pressure reverse osmosis with thermal distillation units powered by low-grade industrial waste heat or concentrated solar thermal arrays. This specific pressure threshold is the primary driver behind current patent filings, with researchers in China and the Middle East funding hybrid architectures that integrate ultra-high-pressure membranes with industrial waste heat. Establishing global freshwater resilience now depends on the successful scaling of these decentralized networks that can manage the thermodynamic tension between renewable inputs and ecological discharge.